I'd increase the mic volume. I'm getting the volume down.
Okay. Hey, everyone, again. Thank you for joining. My name is Sahil, and I'm the president of the Quantum Club. Today, we are going to talk about quantum inspired ML, and this is a technical deep dive in collaboration with AI Society. Uh, Vinayak, who's the secretary of the Quantum Club, is going to be our speaker today. And without further ado, I'm just going to hand over the mic to him. He has some announcements.
Uh,
Class.
oh, I'm gonna do that in the end.
Okay, he has some announcement in the end. Yeah.
Okay, yeah. I mean, it's not much of an announcement. It's like if you find anything today that you see and learn useful, then I highly recommend signing up for Intro to Quantum Machine Learning, titled Quantum Computation, happening next semester from the Computer Science Department. But with that, CSE 598 for graduate students and 494 for undergrads. I'll talk a little bit more about it at the end. But yeah, so before we start, I would like to thank people for two things. One, thank you A Society for like inviting us here and letting and getting us to speak. And thank you everyone for like spreading out. I'll get my exercise of moving like this today. But yeah, so so the talk today is dive into quantum-inspired ML. Uh, a bit of a misnomer. More of what the talk is about today is how do we really do machine learning with quantum computers, and why do we do machine learning with quantum computers? So if I can get you guys at the end of this session an answer to both of these, then I think I've succeeded. Now, uh, there's this like random talk I came across one day which said the special thing about quantum machine learning is that it's hype squared. There's a lot of hype around machine learning. There's a lot of hype around quantum computing. And when they fuse together like Goku and Vegeta, you get hype squared. And so there's a lot of interest in both from an academic perspective and from an industry perspective on that topic. But also there's a lot of misinformation and like misunderstandings about what really makes this field the way it is. So now, as we get started, here's a little bit about me. My name is Vinayak Sharma. I am the secretary of the Quantum Club, but I'm also a PhD student here at ASU. And why I'm talking about this topic and what my background with this topic has been like, most importantly, it's in my research focus, it's my dissertation, but also I've taught this topic a few times before. I've been as I realized today, the only person who has ever TA'd quantum computation in ASU. There's been no other student who's TA'd it yet. I have been invited to teach this subject with my professor, Dr. Aviraj Srivastava at NIT Rourkela, which is one of the premier institutes in India. We taught there for like a week and a half, and we've taught this at a few conferences. VLSI being one of them. We've taught at like DAC. We've taught at ES Week. But yeah, that's just my background and my like history with this field. So before we get into like how we do AI, a more fundamental thing to think about is how do we do computation? What is a qubit? Now, this is going to be a really mathy session, and some of the slides are going to look really scary, but trust me, we'll get through it. It's not that bad. What I really require from you guys is an understanding of what are matrices, what are row and column vectors, and what are trigonometric functions and complex numbers. A lot of these things are already like part and parcel to understanding AI and machine learning, so it shouldn't be too bad. So with that, let's break down what is a qubit. A qubit essentially is the unit of computation in a quantum computer. Now, a lot of us have heard like this idea that a qubit can be 0 and 1 at the same time, but that's a very vague statement. That's like Schrodinger's cat. It's dead or alive, but what does that even mean? What that really means is geometrically, if the binary states of 1 and 0 were points on like perpendicular points on a unit circle, a qubit is every single point in the circle. It is what we call a linear superposition. So when we define a qubit, we mathematically define it as that thing up there. Ket psi is equal to alpha ket 0 plus beta ket 1. Actually, Kostab, I'll take the laser pointer. This is a much larger projector than I'm used to. Sorry, guys. Uh, but yeah, the idea is you can write a quantum state as this mixture. Now, what do these alphas and betas mean? Absolute value of alpha square is essentially, I don't need to connect it, just the laser pointer part. Thank you. Like, I don't need the slide changing part. Thanks. Yeah. So what this kind of means is when you take the absolute value of alpha and square it, you get the probability that when we look at this qubit, you're going to find that it's in state 0. And when you take the absolute value of beta and square that, you get the probability that it ends up in state 1. Now, there's a quick question here, right? Why are we taking absolute value if you're squaring? That seems like a really dumb thing to do. It's because alpha and beta are complex numbers. The square of a complex number is not the same as, is not always positive. Case in point, I square is -1. The magnitude, this is also called, the absolute value is also called the magnitude. I'll be using these two terms interchangeably, is kind of essentially the, how do I put this? Is essentially how long that vector is. It's like its distance from the origin. And when you square that magnitude, it's when you get and square it, you get the probability that the state ket psi is ket 0. Now, that's a lot of math, but like why do we care? Why do we do all of this? It's because in computer science, there's this class of algorithms called randomized algorithms. If anyone's taken like a computational theory class before, they must have heard about this thing called NP problems and NP complete problems. These are a set of problems that are so challenging to solve that any reasonable classical computer, no matter how large the supercomputer is, will take an unreasonable amount of time to solve these problems as the input sizes scale up. But even in classical computation, without introducing any quantum voodoo, there are these class of things called randomized algorithms, which take this principle that if I flip a coin, sample from this like probability, and choose some solution at random, if I just do this much faster process enough times, with some reasonable error, I'm going to get a solution I can work with. Quantum computing takes that to the extreme. And that's where you get things like Grover's algorithm, Shor's algorithm, these very famous names that you've heard in the news before. Now, the other thing that I really want to get through is this is a unit circle. So mod alpha squared plus mod beta squared has to be equal to 1. That is why you can visualize a single qubit as every point on the surface of this circle. The other important thing to note is that a single bit is holding either true or false. The information a qubit is storing is actually stored in these alphas and betas. Even if you say that beta is redundant because of this condition here, a single qubit is holding one complex number, which is almost infinitely larger, an infinitely larger amount of information density compared to a classical bit. And that's where a lot of the power of a qubit comes in. The fact that you can work with these complex numbers and these probability distributions. The other really large part of a qubit we look at is when we add multiple qubits into a system. But do we have any questions about what a single qubit is till now? Yep. Mm-hmm. Mm-hmm. So that's actually a really good question to ask when you think about randomized algorithms. So the question essentially is asking is, for the principle I explained, right, that you can toss a coin and then you pick a random solution, is that basically on the law of large numbers, where if you sample enough times and the number is large enough, you'll see it very often? It's not to do with that for Shor's algorithm. For Grover's algorithm, you actually induce that property. A key part of Grover's algorithm is this idea called amplitude amplification, where if you know some property of the state that you want to like find, you can keep boosting its probability by repeating this procedure to the point where it's the most likely thing that you'll measure, sort of. But yeah, with that I want to talk about another way of visualizing a qubit. So the 2D circle we saw, one of the things that were really like hidden in that is that alpha and beta, those axes, are not real numbered axes. Every point on that axis is a complex number. And as we know, a complex number is actually a plane. So in reality, a single qubit is a 4-dimensional object. But because of that normalization constraint, mod alpha squared plus mod beta squared is equal to 1, in terms of degrees of freedoms or things that we can change, it's actually 3-dimensional. And that is what we call this Bloch sphere. And so what we can think about is, we have gone in terms of representational capacity from a single bit, which is a single point, to the surface of a sphere. And as we know, there are infinite points on the surface of a sphere. So we have literally infinitely more representational capacity in a single qubit than a single bit. But there's a catch, and we will get into that catch later. Actually, we're getting the catch right now. I forgot how I'd organize these. Yeah. The catch is, even though while computing, a qubit has an infinite amount of data or infinite number of states it can be, what you can get out of the qubit is only a 0 or a 1. And that's kind of challenging, right? From a real quantum system, the only thing you can get is measurement. And measurement is the idea that, hey, I want to peek at what your state is. But the moment I peek into it, it's either going to become 0 or 1. So then what do we do? The idea is we do this many, many times. So like we saw, alpha square and beta square are the probabilities of getting zeros and ones. If we rerun our entire computation, let's say 100 times, and we see, okay, 30 times you get ket 0 and 70 times you get ket 1, we can conclude that mod alpha square must have been, with a reasonable level of confidence, 30%, and mod beta square must have been 70%. So that's how you got to get creative in getting information out of qubits. And that's kind of the entire game with quantum computing and later quantum machine learning. Now, a thing here is, while from doing things like addition, subtraction, multiplication, doing it in this probabilistic sense makes no sense, machine learning is a very different beast. As you might have realized, binary classification, for example, only requires us to get like a sigmoided probability at the end, right? We only care about what is the probability of it being in class A or class B. We can easily substitute that with the probability of being ket 0 or ket 1. Whatever the probability alpha square imputes is its probability of being in class 0, and beta square becomes its probability of being in class 1. So there's a lot of things like the fact that, and as we see in the gate computations a little later, matrices and row column vectors are essential part and parcel of quantum computers, are also the building blocks of AI. And that's one of the things we see throughout this talk, that a lot of the things that make AI what it is are fundamental building blocks of quantum computing. Oh, it's not just probabilities. You can get other useful things you can do AI machine learning with are expectation values, probabilities as we discussed, variances, counts, all of these statistical measures that we can naturally extract by repeating a computation multiple times. Okay, so expectation value is the idea that if I have, let's say, probabilistic variables, right? Let's say a rolling of a dice. Expectation value essentially returns what is the number that I'm most likely to observe from rolling a dice. And the way that's calculated is whatever the values are, so like I times its probability. So in an equally weighted dice, it would be 1 times 1 by 6 plus 2 times 1 by 6 plus 3 times 1 by 6, and so on. And so that's the idea of expectation values. Do we have any other questions? Yep. Okay, that's a good question. So the question is, why do we say that repeating something multiple times gives you a better value? Okay, imagine if I don't like Kostov. I like him, he's my lab mate, but imagine I didn't like him and I wanted to mess with him. I gave him a unbiased coin, but I told him the coin is completely biased. And he has to figure out whether it's biased or unbiased in exactly 3 throws. Can he ever figure out that the coin is unbiased? No, because at 3 throws, you're either going to get something that's always giving heads, or it's giving 2 tails and 1 heads, or 2 heads and 1 tails. And there's also all 4 heads, but you get the idea, right? You're either going to get 100% or 66 point whatever percent as the probabilities or as the biases of the coin. As you keep flipping this coin over and over and over again, the actual counts that you get start getting more and more in line with the probabilities, because having these biased distributions, the probability keeps going down exponentially as you keep increasing the number of throws. Because let's say I do 1,000 throws and it's a completely unbiased coin, the probability that you get all heads for all those 1,000 times is 1 by 2 to the power 100. And so that's an exponential drop for these Lorry bias distributions to show up. And that is kind of the game. The more times you repeat a probabilistic experiment, the most probabilistic outcomes show up a lot more times. And so you get much better estimates of things like variances, probabilities, and so on. But yeah, good question. I hope that also answered the question. Yeah, yep, yeah, yep. The expectation value is about the value you observe and not about the probabilities of the states. So when you have like a die, right, if you have an equal chance of getting 6, if you are doing additions all the time, the value you would most likely observe is around 4. Because everything is an equal value and now you're weighting on terms of actual value. That's the thing with expectations. Right. Before we go into how to compute, we need to also understand this tiny little math concept called a unitary matrix. A unitary matrix is a very special kind of matrix because of 3 specific properties. Number 1, unitary matrices are always guaranteed to be invertible. What does invertibility in matrices mean? As a quick refresher, it will be easier actually if you move there, it will be easier for you to see. Sorry. Yeah, but like unitary matrices are like the idea is, sorry, an invertible matrix is one where, so if A is a matrix that exists a matrix A inverse such that A times A inverse is identity. That is the idea of invertibility. And not every matrix is guaranteed to have an inverse. Unitary matrices are. The second is unitary matrices are guaranteed to be square matrices. And the third, which ties into the first property, is that it just so happens that the complex conjugate transpose of a unitary matrix is its inverse. What is the complex conjugate transpose of this dagger symbol? You transpose the matrix and apply the conjugate operation on every element. So let's say the matrix was just A was equal to I, A star is minus I. If C is equal to A plus IB, it's A minus IB. And so you transpose the matrix and then do the complex conjugate, that gives you the dagger of a matrix. And for unitary matrices, the dagger times the matrix itself is always the identity. So the dagger or the complex conjugate of a unitary matrix is its inverse. The second, an outcome rather than a property of a unitary matrix is that a unitary matrix is angle preserving. You know, you can always find the angle between two vectors as long as their dimensions are the same, right? So if you have a vector in 2D with x0, y0 and x1, y1, you can always find the angle that they make when you draw them to the origin. The thing with the unitary matrix is when you apply this matrix to any two vectors, the same matrix, the angle between them doesn't change. This should give you a hint as to what unitary matrices really do. Yeah. No, they actually rotate. So if I rotate two vectors by 30 degrees, both of them by the same angle, the angle between them never changes. And that is the game with unitary matrices. And it just so happens that every fundamental gate in quantum computers is a unitary matrix. There's a really good video by this channel called Quantum Sense, which kind of explains why it ends up becoming this case. But for the purposes of this like much more condensed 2-hour talk, you have to take me to my word. I promise I'm not lying to you guys. But the idea is unitary matrices are the fundamental gates of quantum computers. So here are some really famous ones, right? The Pauli X gate is like the equivalent of a NOT gate in classical computing. Now, one thing I kind of should have put in the slides and have not, and I can't use the board right now, is that what these kets are hiding is that each one of these is a column vector. A ket 0, oh, maybe I can fit it right here somewhere. Nope. It's like a ket 0 is equal to 1, 0, and a ket 1 is 0, 1. So ket 0 is the column vector 1, 0, and ket 1 is the column vector 0, 1. So what ends up happening here is, as you can see, Hadamard times ket0 is going to essentially just do this matrix multiplication, which yields the state here. This is called an equal superposition. Why? Because if we apply that mod alpha, like absolute value of alpha squared and absolute value of beta squared rules here, the probability of getting ket0 from the state is exactly half, and so is the probability of getting ket1. So the cool thing here is that you notice every single gate from this example being a matrix and every single state being essentially the a column vector means that every computation in a quantum computer is equivalent to a matrix multiplication, specifically a matrix vector multiplication. That is extremely similar to AI. If you think about a dense layer in a neural network, the weight matrix is a matrix and the data going in is a vector. So remember when I said that a lot of things that are native to quantum computing also are native to AI? This is what I want you guys to constantly remember. Do we have any questions? One more thing I point out is I alluded to what I said earlier that the X gate is like the NOT gate. If we apply the matrix ket0 to this matrix here, you'll get ket1. And if you apply ket1 to this matrix, you'll get ket0. Now, unlike classical gates, right, where the AND gate, NOT gate, and those gates, quantum computing has these things called, these again, yep, has these things called parameterized gates. And this is where things get really interesting. So, like I said, every unitary matrix is a rotation, right? And if every gate is therefore also a rotation, we can define axes. So in that big block sphere we saw earlier, there are three fundamental gates, Rx, Ry, and Rz. What they're essentially doing is, the Rx gate is, like if you take this x-axis in the block sphere and you rotate it by an angle theta using that axis, is what the Rx gate does. Similarly, the Rz gate, you can see here as the rotation is going around, is like if I grab this sphere by that z-axis and then rotate around it. These three are universal. So using these three gates, you can convert any quantum state into any other quantum state. And you can, by some combination of these three gates, create any single qubit gate. Similar to how like the XOR gate is universal in classical computing, these three are universal in quantum computing. With the catch being, in classical computing, the universality comes from different arrangements of XOR gates. In quantum computing, the universality comes by different parameterizations of theta. What I want to take is a moment to like think about this idea, right? You have this thing that can create any universal, because gates are the functions in quantum computing, right? So you have something with different parameterizations can give you any function. I'm sensing the word universal function approximator somewhere here. So I'm just leaving you guys with that like word again. Yep. Mm-hmm. Okay, so there are two parts to your question, right? The question is how do we choose the right theta, and uh, the other one is how do we actually adjust the qubit. The first part of the question is it depends, right? If you're doing it for a known gate, you can solve a bunch of equations to figure out what theta should be based on how you want the gate output to be. So for example, this Hadamard gate, right? It gives you an equal superposition between 0 and 1. A similar way to achieve that is just Ry theta is equal to pi by 2, because that will yield pi by 4 in these matrices. So you'll end up getting pi by 4, pi by 4. So pi by 4, pi by 4, minus pi by 4, pi by 4. It's not exactly the Hadamard matrix, and there's a reason because the Hadamard matrix is actually Rz and Rx, but you can solve systems of equations to get these values. The other way to do this is the machine learning approach. Hey, I know what my output should look like from data. Let me just use gradient descent to figure out what these theta should be. And that's what we do actually down the road in today's presentation. Yep. Any gate, not number. Yes. That's also a good question. So can the same gate have a different combination of these three? Ordering, yeah, actually no, because two things. Matrix multiplication is not commutative, right? So A times B is not equal to B times A in matrix multiplication. Second, uh, the second point is these are very different matrices. So when you have a specific matrix for a gate you're targeting, like the Hadamard gate, for example, even if I can use Ry pi by 2 to get 0 to 1 by root 2 plus ket 0 plus ket 1 and ket 1 to like 1 by root 2 minus, what kind of ends up happening is, think about this, right? If I rotate using Ry pi by 2, I get to this point here, right? And then I apply that again, I get to ket 1. This implies that Hadamard times Hadamard of ket 0 is ket 1. But when you actually see the Hadamard matrix, if you apply this twice, this is a special thing called a Hermitian. It's its own inverse. Hadamard ket 0, so Hadamard of Hadamard is just identity. So Hadamard ket 0 gives you this thing called the ket plus state, this thing. And if I apply Hadamard to this, what you get is ket 0 again. So even though you see similar behaviors, it's not the exact same gate. There's only one specific factorization that leads to the exact gate. Now, this is not a universal rule. Some of them might have multiple, but as a rule of thumb, normally you can't assume that. Yep. Okay, so there's two parts to this, right? So the question is, what is the ultimate purpose of doing so much matmal? First part, you don't actually, a quantum computer is not doing this via matrix multiplications. A quantum computer, actually, I should have answered your second question and I should have cleared this out. Like, how do we do this on a real quantum computer? On a real quantum computer, each of these matrices correspond to a different laser pulse, depending on the way that the quantum computer is made. Like different companies make it different ways. Google, IBM, they make it using this thing called superconducting. Quantinuum, Rigetti, these guys make things called optical quantum computers. And so the physical phenomenon that induce gates changes. But the idea is these are all induced by physical energy pulsations. Now, why are these useful? We get into once we start getting multiple qubits. So if you can like hold on to that, then you get, hopefully you get a better answer to that. But yeah, the idea is that these are the gates and these are the units of computation. You can take any quantum state to another quantum state using these gates. And so these are essentially the functions in quantum space. The next thing I want to think about, oh, I've already covered this actually, the idea that these three gates are completely universal and you can create any gate using some combination of those three gates. So this gives us actually a really good building block for machine learning, right? Even at a gate level, if I don't know, even if I don't know what is the right set of gates to go from some quantum state to another quantum state is, because of universality in parameters of these three gates, I can recursively keep applying these three gates and learn these theta parameters to do machine learning with a single qubit. With that, I want to give like a visualization of what a Bloch sphere looks like and what these rotations look like. Just to give some kind of context, it's kind of helpful. Let me just open up this. Yep. So if I have like a quantum gate here, like the known quantum gates, right? If I apply the Hadamard gate, for example, like we saw, it's actually this kind of like off-axis rotation which is done via two other rotations. And it's useful because if I apply this again, you see what it ends up doing is it gives me back to ket 0 with this weird upper half rotation. If I apply the X gate here, it's kind of slow. It goes all the way down to ket 1. Now if I apply the Hadamard here, you see it just shows up here on the other side. And that's kind of the game here, right? Even though these gates are rotations, they're not always rotations around that axis. But by combining rotations on these three axes, you can simulate any gate. And this is just like there's another like self. I'm going to do a shameless plug here, guys. If you're more curious about what this Bloch sphere really is, I have a blog post about it on my blog. There's a lot of animations. I put in a lot of work into this. But this takes a geometric perspective into explaining why the Bloch sphere is the way it is, and how do you go from like that C4, that two complex axes, to the Bloch sphere, and why we end up doing some weird things. Because one of the things I didn't point out is from the matrix, from the vectors of ket0 and ket1, they're clearly perpendicular, right? And how do I prove that? I take the inner product. But on the Bloch sphere, these two end up becoming completely on the same axis. They become collinear. And that's not a very normal thing to do. At first glance, it looks like you're doubling angles. But if you go through that blog post, if you're free and you're interested, what you see is what actually ends up happening, and I'll do that in the animation down here, is that the space actually starts transforming this way. We go into something called a projective space where multiple axes show up as the same axes or the same axis. And so yeah, that's kind of how I'm saying the Bloch sphere is kind of weirder than it looks. And yes, shameless self-plug. Yeah. With that, I want to bring in this the last concept from single qubits that we'll be taking is this thing called the measurement postulate. Measurement is a very destructive, sorry, one last note. So remember how I said unitary matrices are always invertible and that every quantum gate is a unitary matrix? What that kind of results in that every operation in a quantum computer is completely reversible. So given the output and the set of inputs, without exception, I can always, the output and the set of operations, without exception, I can always find the input. This is not the case with a classical computer. I can give you an AND gate and its output and you cannot tell me what the input was. So that's actually a challenge and a really interesting thing about quantum computing is that everything is reversible. There are other many interesting properties that we don't have time to go over, like this thing called a no-cloning theorem, where you can't copy arbitrary quantum states. If you're interested in those, join us at some of the lectures that we give in the Quantum Club, and you can take the CSE 500, 594 or 494 course for credit. It'll show up on your transcript if you're interested. Yeah, so the measurement postulate is this idea that after the first measurement, whatever you see, it collapses the superposition. So the idea is after the Hadamard gate, if M1 is ket0, no matter how many times I measure after that, it's always going to be ket0. That is the idea of the measurement postulate, that measurement is a super destructive operation. So if I have to rerun that computation multiple times, it's not that I'm doing measurement multiple times, it's that I have to apply the exact same gates again and again. With that, we move to the idea of, I mean, I would love to go over the code, but I think we don't have time for that. So we'll only do the code for the actual machine learning part of this. With that, we move into the idea of multi-qubit systems. So till now, we've already covered the idea that a single qubit holds infinitely more information than a single bit. What we see as we go into multi-qubits is that the size of these vectors also increases exponentially. And all of that is because of this really very badly named operation called the Kronecker or the tensor product. The reason I call it badly named is because the word tensor product actually has been used for to describe multiple things. In machine learning, it normally talks about matrix multiplication for higher dimensional matrices. In quantum computing, what it refers to is this thing called the Kronecker product. So if I take a 2x1 column vector and then do this Kronecker or tensor product with another 2x1 column vector, what I get is a 4x1 column vector. Because the way the operation works is it's a combinatorics operation. So what ends up happening is every possible combination of these values gets listed as a flat vector, and that is the Kronecker product. So what ends up happening is, if two qubits have a 2x1 column vector state, or a basis state, a single qubit, two qubits have a 4x1, three qubits have 8x1, and so on. N qubits have a 2 to the power n dimensional vector as their column vector. And so when we start doing these matrix multiplications, you go from 2x2 matrices to 4x4, 8x8, 16x16, 2 to the power n cross 2 to the power n matrices, which becomes, for obvious reasons, super expensive to compute if you're doing these classically. So a huge advantage in quantum systems and quantum machine learning in general is that you get access to exponential feature spaces. When you guys study machine learning, you must have heard about this thing called the curse of dimensionality. As the dimension of the vectors, and this is especially true with transformers now, but as the dimension of these vectors increases, the computational cost increases at a very alarming rate. Quantum computing kind of sidesteps that. Why? Because like I said, a quantum computer is not doing these things as matrix multiplications. It's doing all of these things as physical operations. So when you learn, and as you might have learned, right, the size of a vector in machine learning makes it more expressive. You get exponential expressivity in quantum computing. Why? Because also remember, these vectors are not real numbered vectors, these are complex numbered vectors. Any questions while I drink water? I'll give this, like, I know I've info dumped you with a lot of information, guys. So first, thank you for still being here. And like, I'm hoping you guys are like enjoying and learning things. But also I'm going to give you some time to absorb this information before we move to like the computational aspects of these things. So just, yeah. Mhm. Mhm. Okay, so the question is, I like my like the understanding was that quantum computers store these into this information into laser pulses and things. That's not true. So the thing is, all of the equations that we're studying here, rather than think about them being stored like a hard disk in laser pulses or magnetic fields, these are actually the equations that govern quantum mechanics. So the evolution of a quantum system is governed by these equations. So it's not like this data is being stored somewhere and then being called and being computed that way. It's more like when we take a quantum field, a quantum system of let's say 3 qubits, right? And let's say these are electrons. The spin up and spin down of these electrons are going to be your ket0 and ket1 states. As we apply these laser pulses to the electrons, the way that that system evolves and the way that the wave function that you've heard of and the way that when we measure these electrons, things evolve are actually modeled by these equations. So it's less that we're storing this data in laser pulses like a hard disk and then pulling them and applying computation. It's more that the fundamental mathematics that explains these physical phenomenon can be hijacked to do this computation. So we are going the opposite. Instead of simulating physics using computation, we are simulating computation using physics. Yeah. Mm-hmm. Mm-hmm. Yeah. Mm-hmm. Mm-hmm. Right. So there are a few questions there to unpack, and all of them are like questions worth asking, right? The first question there is, uh, like if a classical computer is using computation to understand reality, right? You kind of know what you're trying to model, and you're trying to get equations to model it. And here you're doing the opposite. So how do you do that? Why is that useful? So an example of this is Shor's algorithm. What it's actually doing is it's saying that we want to find the factors of this, the prime factors of this super large number, right? Now the thing with uh, uh, the idea of finding factors that Peter Shor kind of realized, or actually people knew for a while, is that it's actually a periodic function. The remainder of a number divided by another number is a periodic function. Let's say you have the number 3, right? Every time you get the output of the remainder, you either get 0, 1, 2, 3, 0, 1, 2, 0, 1, 2, it keeps repeating, it's a periodic function. So finding the divisor or the period of something can be, finding the divisor of something can be reduced to the problem of period finding. You can write a set of quantum gates, right, here, which essentially make it so that when I measure out my state in many, many qubits, Each of those values corresponds to a specific period. And the value that I measure with the highest probability is going to be the period of the prime factor. And if you find one prime factor, you find the other. That's kind of obvious, right? Because you just divide. So the idea here is you can actually co-opt these processes. If you understand the matrix structure underlying, you can skip the really expensive large matrix multiplications with those physical processes. So if you set up your problem in a way that can be solved using these large matrix multiplications, for example, machine learning problems, then instead of doing the matrix multiplications themselves, you can apply the physical pulses. Those happened on an order of microseconds. 1024 cross 1024 matrices happen on a matter of seconds. That is still just 10 qubits. Once you get to 30 or 40 qubits, you're looking at 2 to the power 40 cross 2 to the 40 matrix multiplications. Another very basic thing that we learned really early on is that you can solve systems of linear equations using matrix multiplication. You can do that using a quantum computer. There are equation solvers based on quantum computing. Yep. Yep. Uh-huh. Mm-hmm. That's not really the big problem. The bigger problem is okay. I think let's have answer this question after we understand how computation with multiple qubits actually works. That will clarify some things, right? So when we go to multiple qubits, there's one way to like understand this state is this idea that if a single qubit is a point going between a line, it's a gross simplification, right? But if you're only thinking about the probabilities, then 2 qubits becomes a square, 3 qubits becomes a cube, and the basis states ket00, ket01, all of these sit on like on the edges or the periphery of this square. This is a gross oversimplification because we can't really visualize things greater than 3D. It's just a limitation of the human mind. But what this is kind of trying to illustrate is that as we increase as we increase qubits, we add exponentially more dimensions in the vector space or the feature space, which from like representational points of view is super useful. From a computational point of view, right? Exponential power, but are we doing exponential cost? What this kind of like is hiding, or like kind of like behind. Sorry, 1 second. Sorry, guys. In a session. Yep. So what that's actually hiding behind us is two kinds of gates. You have native multi-qubit gates, like the CNOT, and you have compositional gates. So like we explored earlier, to get the state vectors, the ket00s and the ket1s, we apply the Hadamard product between two single qubit states, right? We can do the same thing with gates. If we want to apply, let's say, a Hadamard to a 2-qubit system, we just tensor product it. So to your question about finding like really the exact frequencies, if we have a set of predefined gates, like the Hadamard gate or the RY gate and RX gates, we can apply them to single qubits to see ripple effects on the multi-qubit states. That's one way. The other way to do it is with native multi-qubit gates like the CNOT. This cannot be factorized at all into these 2-qubit gates. And this specific gate, what it does, I think I have it in the next slide. Oh, I'll have it in the slide after this. So just understanding what these compositional gates are doing, right? The compositional gates are saying that, okay, if I want to apply, let's say, this kind of a computation, where I'm applying, let's say, to 2 qubits the X gate and the Hadamard gate, and then again to 1 qubit I'm applying the Hadamard gate and nothing. It boils down to essentially these 4 cross 4 matrices. Why am I saying 4 cross 4 matrices? Because this is a Hadamard product. 2 cross 2 matrices become 4 cross 4. Any questions about just this part right now? The idea that we can boil down applying single qubit gates to multiple qubits to the Hadamard product here. Okay, so, oh yeah, if you have a question, okay. So I'm assuming we're all good with this. So coming to the more interesting point, right? Coming to the idea of, oh, I don't have that slide, what? Oh, it's for some reason got reordered. Yep. Coming to the idea of native multi-qubit gates, you mostly for native multi-qubit gates, you have exactly two types. You have controlled single qubit gates or the CNOT gate, which is also a controlled single qubit gate. The idea is what these native multi-qubit gates do is they say that I am going to conditionally apply a single qubit gate. The CNOT, for example, says that if this qubit with the black dot, known as the control qubit, is in the state ket1, then I'm going to apply the NOT gate to the to qubit 2. So things like ket00 go to ket00 because the control is 0, nothing happens. Same for like 01. Because my control qubit is in state ket0, nothing happens. But when my control is in state 1, the target qubit gets flipped. And this is not just limited to the flipping operation. You can have a controlled Hadamard gate, for example. These are native multi-qubit gates. So even though you have these super large matrices, as long as you know the individual independent operations, you can just do it on those single qubits, the relevant qubits. Which is why you must be seeing I've implicitly been drawing quantum computing in these circuit diagrams, where every qubit is represented by a line, and the operations being applied to them are represented as the matrices or the symbols on that line. And this is how we normally do quantum computation. And when we and again, if I could show you within the time and actual algorithm, things would be much more clear. But the idea, and if you're interested, please do come to one of our talks. But the idea is you can break down algorithms in this language of state vectors and then scale that up. Now, I am not a material scientist, so the actual physical implementation part admittedly is completely out of my area of expertise, and that requires advanced material science and like physics degrees. I am more from the computational mathematical background. And with that, we can extend to any number of qubits. Essentially, you can have multi-controlled gates that when all of these qubits are in state 1, then we are applying this unitary here. Now, what is super interesting here is the idea that this applies to superpositions. It's not like a truth table where I'm reading out values. It's that it's applying when my state is a mixture of these other states. So you can see if I give A ket00 plus B ket101 plus C ket10 and D ket11, and I apply my CNOT gate, it just completely transforms. So the amplitudes themselves are what are swapping here. So C has now become the amplitude of ket11 and D has become the amplitude of ket10. Now this is a special thing called an entangled state. What is kind of unique about this is you can no longer ever separate these states out, in the sense that you cannot write them as Hadamard product of single qubit states anymore. And you have induced all of this, you've induced the state with only a 2 qubit gate and single qubit gates. Yep. Hmm? This is still reversible. So if I apply the CNOT to this again, you see I get my state back. Right? Reversibility means I can apply operations to get my input back. It doesn't mean that the input doesn't change. So I cannot write this state alone, I cannot write as a Hadamard product of two single qubit states without applying the operations in reverse. So as long as I specifically don't go out of my way to apply those operations in reverse, I have this classically a state that cannot be classically simulated without exponential matrices. The last part of this is multi-qubit gates are also universal. Combinations of the CNOT gates followed by multi-qubit by the single qubit RY, RZ, RX gates can simulate any multi-qubit gate. And this is where quantum machine learning actually starts getting very interesting. If you apply multiple layers of CNOTs and RY, RX, RZs, you can do any multi-qubit, you can learn any multi-qubit computation. And with that note, let's actually look at multi-qubits here, like machine learning with quantum computers. I'm assuming that's what a lot of people came here for. And sorry I delayed it so much, but I'm hoping that what we learned up till now was somewhat useful in both motivating why we look at these, why we are interested in quantum machine learning to an extent, and what is the apparatus for it. So guys, what do we really need in anything machine learning, right? What are the ingredients to a recipe known as machine learning? The first ingredient is something trainable. That comes from our quantum computing side, which is parameterized gates. The next ingredient is something nonlinear. Uh, I trust that the AI Society has done a good job because I know these guys and they're really good at what they do. So they've taught you why nonlinearity is important. And without nonlinearity, you end up with like really bad machine learning models. In quantum computing, that nonlinearity comes from measurement. Which if you remember, measurement is magnitude squared. Then you need something, then you need something of a loss function. We can just use classical loss functions. The only catch is that the loss functions have to be designed around the measured quantities. So the loss functions either have to use probabilities, expectation values, or counts, or standard deviation. And finally, you need an optimizer. Again, we can just take that from the classical machine learning side. And so this is where QML becomes the intersection of classical computing and quantum computing. So classical machine learning. You take the loss function and optimizers from classical machine learning, and you take the trainable parameterized gates and the nonlinear measurements from quantum computing, and then you get this like, I wouldn't say unholy, but like this really weirdly interesting love child that is quantum machine learning. So let's let's think about the most basic thing you need for this idea. The most basic thing you need is to somehow get classical data onto a quantum computer, right? The easiest way, or one of the most common ways to do this, is this thing called angular encoding. The idea is if you have a classical vector of data, x0, x1, x2, whatever, through x0, you just rotate individual qubits by that value. So if you start from a state ket0 and you want to get the number 23 into our state, you rotate by 23 degrees. Side note, if my professor ever finds out I'm using degrees, he will murder me because he really hates the idea of degrees. And the more I work in science, I agree, radians are way better than degrees as a unit. But yeah, the idea is you can rotate by that number of degrees. And what this kind of creates is this really interesting state. I did not, for the sake of like A, my laziness, and B, our own mental sanity, I didn't write out the full Hadamard producted quantum state here because that would be 2 to the power 4, 16 different values. But you can imagine that what you get from this data encoding is this super long, super non-linear function in these x values, right? This is something also we want from machine learning in general. Non-linear function combinations of our input data. And this is the encoded state that we get from all of this. And this is also a really like super condensed notation. If I write ket0 to the power tensor n, that just means I have n ket0 states. The next thing we kind of need is something to like learn from. And as we like, another way we can actually encode data, sorry, this is a different one. So we can also encode data onto a single qubit. In like 2022, there's this gentleman whose name I cannot for the life of me pronounce. They came up with this thing called the data reuploading classifier, and what they prove is that in a single qubit, you can make a universal function approximator or universal classifier at the very least. And so another way to think about encodings is the path of a qubit across the block sphere. So my first value here, 4.55, is going to take me from ket0 down here. Oh, the ordering and coloring don't match, they're supposed to. But like my first rotation takes me down, and then from there I go to this red vector here, from there I go to this yellow vector here. So my rotations or my data functions, input data, becomes the path that I'm tracing on the surface of the block sphere. To really understand why quantum machine learning does what it does, a thing I really want to introduce to you guys is this idea of a feature map. If you have this data here in two classes, green and blue, and I'm telling you can only separate it with a line, you're going to do a pretty bad job, right? Because this is not linearly separable. But if I push that data down into 2 dimensions in using a parabolic function, for example, suddenly I end up with a linear decision boundary. There's this thing in math, which again, I don't really have the time to prove, but I need you guys to trust me. Again, I don't lie to you guys. Uh, is this idea that every nonlinear function is actually just a linear function in much higher dimensional feature space. Sort of. The derivation for this comes from this thing called the RKHS, the reproducing kernel Hilbert space. I mean, I don't know how many of you guys have studied like vector algebra, but vectors are really wide things. Normally in machine learning, you only deal with vectors as like columns of numbers, right? But formally in mathematics, functions are vectors, series are vectors. You only need to satisfy 2 specific properties to be a vector. So anything can be a vector really, and any set of vectors can be a vector space. So yeah, the idea is you can make anything in higher dimensions a linear decision boundary. And if you guys remember learning logistic regression, the only thing you really need from higher feature space is the inner product or distance between points. Because your loss functions are only based on these ideas. Have you guys studied how many of you have come across an SVM before? A support vector machine. So like 3 people. Now in the support vector machine, there's this thing called the kernel trick. The kernel trick introduces some non-linearity and then does linear classification. The data encoding alone in a quantum computer is similar to a kernel trick. Why? Because we go from n-dimensional data to 2 to the power n-dimensional data with non-linearity already built in. Now, this is another thing. I really dislike the fact that the support vector machine called that the kernel trick because a generation of people misunderstood what a kernel is. Whenever I talk to someone who comes from a machine learning background, to them a kernel is this non-linear mapping. That is not true. So what is a kernel? So a kernel, I'm going to just go through the animations and then explain this one by one because I don't really want the animations. So the idea is this. The function that takes you from lower dimension to higher dimensional feature space is called the feature map. The kernel is what helps you apply a shortcut to compute that inner product efficiently. So for example, if I consider a feature map which takes phi of x comma y to x square root 2 xy and y square, right? And I want to compute their similarity. A similarity, if you remember, is computed via the inner product, which is this computation here. So this row vector transpose times this column vector, right? Or technically this is written in a weird way, but this is supposed to be a row vector times a column vector. It boils down to this computation here, which if I factor out other terms, was actually just this value in disguise. What is this value? This is just the normal inner product between those 2 original vectors, but I'm squaring it. So what ended up happening is, in this 3-dimensional space, the inner product, the only thing we really care about, can be calculated by just squaring the inner product in lower dimensional space. And that is the kernel function. Which is why when we actually see kernel definitions in mathematics, it's not phi of x, it's k of kappa of x comma y, or xx dash. Because the kernel function is actually just computing similarities. It's not computing the higher dimensional map. Why is any of this relevant, right? All of this is relevant because when we start building up a quantum neural network or a variational quantum model, what we see is it's actually just a kernel, but a kernel with exponentially large feature spaces. So this is the basic anatomy of a variational quantum model, one of the most ubiquitous of the basic types of quantum machine learning models. You have a data encoding layer here in yellow. This is the static data encoding. Oops. I can't remember what had animations and what didn't. Sorry, guys. But like the idea here is, this is the starting where I'm putting the input to my model. Then like any good machine learning model should, we have some layers, right? These layers, essentially, as we look later, are combinations of these entanglement patterns, which are CNOT gates, and the parameterized gates RY, RZ, RX. So like a good therapist, let's look at the layers. Let's get in deep. So our idea here is, within this like really compact representation or notation, what we have is an Rx, Ry, Rz gate, and some pattern. And this pattern, this is the most common one called cyclic, because what it creates is a fully entangled state. Because why am I saying it's fully entangled, right? Qubit 1 is now dependent on qubit 0. Qubit 2 is dependent on qubit 1. And now qubit 2 is, and qubit 0 has now become dependent on qubit 2. You can't really tell who's dependent on who anymore. I really should have put that at the three Spider-Man pointing meme here. But yeah, the idea is you cannot tell who's dependent on who anymore, so everyone is interdependent. That is a fully entangled state. As I told you earlier, right, when I combine these building blocks and I apply them multiple times with different parameters, I can learn any quantum function. And that's the basic idea behind this this formulation of a quantum machine learning model. But when I look at it from a classical geometric perspective, we couldn't go through the math actually. This would be really cool. So normally when we are going through like quantum computing math, we put these things called barriers and number them to like properly understanding what our gates and states are doing. So at the end of the first two gates, right, at this point here, what I get is this really long state vector, which, as I talked about earlier, is a super complicated trigonometric function of our input data x and y. To that, I'm going to then apply my next level of gates. And now you see, essentially what I get down here is a function of data and trainable parameters, just like any good machine learning model should be. Especially after the C0, because what the C0 does is now, you see how we had these really nice, easy to handle 2x1 vectors being separated by this Hadamard product? After C0, we don't have that anymore. And it's not possible to do that anymore. Yep. Now what I wanted to like build towards, and there are like supplementary slides which I don't think we'll have the time to get into, but what I really want to like impress upon you guys here is, under the hood, from a machine learning function approximation mathematical perspective, what these models are really doing is two equally mathematically valid things. One is it's working as an optimal data encoding, where what I'm saying is after measurement, my separating hyperplane is fixed, which is the computational basis or the z-axis of the block sphere. I'm saying I already know what my separating axis is in this higher dimensional feature space, and all I want to know is how do I arrange my data points, input data points around this separating vector. So that is the optimal data encoding interpretation. The other completely mathematically identical and valid interpretation is my first step, that yellow step there, is placing the data randomly within this higher dimensional feature space, and then I'm just trying to find what is the right way to cut my feature space to do a linear separation boundary. And what is really interesting is mathematically these are equivalent, which means that just that yellow step in step 1, that yellow part there, already creates linearly separable data. Because the arrangement essentially says that it wasn't linearly separable, I'm arranging them in that way. But what optimal separating hyperplane is saying is I'm finding the plane. What these thetas are doing is it's finding that plane. But the plane must have already existed to begin with. Otherwise, you wouldn't need to do this like mapping part. And that's kind of the cool thing. What we're essentially seeing with both of these models is that just the act of data encoding creates a linearly separable data set, which is super valuable from a machine learning point of view. Let's put this idea into code and see how this kind of works out, right? Let me first set up what we're trying to learn. So we could have learned from some real-world data set, but I found it would be a little bit more interesting from a quantum machine learning point of view is if I essentially have these two data points that come from a uniform distribution between 0 and 2 pi and apply a random set of quantum gates, a set of gates that I don't know what they are, and then I measure and say that the sign value of this measurement, don't worry about why the measurement looks like this. If you're interested, please come to class, I'll show you why. But like, don't worry about it for now. If I take the sign, and the sign of this is going to be, this value is giving you a number between -1 to 1. And I say that everything in the positive sign is going to be the blue class here, and in the negative sign is, sorry, positive sign is the orange class here, and the blue sign is this, and the negative sign is this blue class right here, you get a data set which looks like this. It's a completely non-linear separation boundary, right? This is a curve. So now what we want to do is we want to design a variational quantum algorithm which kind of learns what those gates are. From data, it's trying to re-find out what those original set of quantum gates were. So how do we build this thing, right? This is built in this library called PennyLane. We first write our data encoding block. It's super Pythonic. I'm applying, like I showed in the diagrams, RY gates, and like a good Python function, I'm taking the inputs as just the arguments. From there, I'm going to for loop over the layers. This is our variational circuit. And just for funsies, I kept doing this alternating CNOT pattern because it's only 2 qubits. So every even layer I have qubit 0 dependent on qubit 1, and odd layers qubit 1 is dependent on qubit 0. Very healthy couple, these two. looking at this again, we go over the layers because the weights have a shape which essentially is number of layers, number of qubits 3. We loop over the outer shape of the weight matrix, and then we apply this ROT gate. This ROT gate is just a PennyLane shortcut to doing RY, RX, and RZ. Actually, technically it's RZ, RY, RZ. Mathematically, it becomes equivalent for reasons I won't get into. But the idea is we apply those 3 single qubit gates, and then we apply our CNOT pattern. Finally, we return the expectation value with respect to ket 0, ket 1. And with all of this, we get something that we're ready to do machine learning with. So does it actually learn? Is learning actually happening? So what this diagram is showing here is like the overall flow. This is our feature space before training. How do we get this feature space? We use random weights and we plot it out. We apply a training over the binary cross entropy loss function. Why can we do binary cross entropy? Because this is a probability function. It's a probability distribution like sigmoid. We get values between 0 and 1. We can just apply binary cross entropy. And what I'm telling you, and as I'm going to show you in a bit, what we get at the end is something that looks extremely similar to our target function. And what does this look like? Just look at the video down here. Over different epochs of training, our feature boundaries here is evolving. And finally, by the end of our training procedure, we get the final target function. And now if we take those thetas and plug them back into our layers, we can multiply all these matrices to get back the original unknown gates that we had applied to our quantum state. Epochs? This had around 105 steps, which was equivalent to roughly like 5 epochs. Yep. Yeah. It's both. So what ends up happening because of the way measurement works out, modeling because we're using the same input data, all you're learning is a classification pattern. So you're seeing everything on one side of this weird circular elliptical eye shape. Everything on the outside is the blue class. Everything on the inside is the orange class. Now, whether you're saying that's me learning a decision boundary or learning the distribution, you can't really differentiate the two in machine learning. Any other questions about any of this? It's as good or as bad as a normal machine learning model. Outliers will have similar effects to machine learning because the loss function is going to treat the gradients like at a commensurate rate. And with that, we actually made it to the end. I will do questions, don't worry. Yeah, actually now I'll do questions. Yep, what's up? Mm-hmm. Oh, okay, so let me rephrase that phrasing. I'm saying in terms of outliers or in terms with like the properties on how outliers affect the learning process, it's similar to classical machine learning models. But there are like theoretical papers which have shown that QML models can learn a much larger category of functions than classical models. Not in the least because QML models can actually learn complex numbered functions, which classical models really struggle with. The main representative power really coming here is from the fact that when you get into these exponential dimensions, you learn a very large variety of really complicated functions. Now, if you're interested, I do have slides about how mathematically those two are equal. But I think before that, I want to go through a couple of announcements. Uh, Sahil really should have been here for this, but announcement number one is please check out the Quantum Club, guys. Uh, Hint, all my announcements are just essentially shameless self promotion. But yeah, the idea is please do come check us out at the Quantum Club. We kind of like aim to educate and like get people interested in a wide variety of things like quantum computing, quantum machine learning, quantum sensing. Quantum computing might still be a long way away. Quantum sensing is utilized extensively today. Sahil, do you want to say anything about the Quantum Club? That we do quantum sensing communication, then please check us out.
Yeah, I just want to like also highlight our next event. So Vinayak talked about like optical quantum computers, right? And he mentioned Quantinuum. So we are actually going to have Mark Jackson. He was the senior evangelist for the for Quantinuum, who's going to come on 25th and give a talk. So if you want to hear him, that would be great. Like, come join us at this room actually on 25th at 6 p.m.
Those are spoilers. We haven't announced that yet.
Yeah, we will very soon, but yeah. But yeah.
Yeah. So the other thing that I'd like say, the most recent event, if you remember, Sahil, is happening tomorrow. Is so we've been doing over the last semester an entire series which goes into more detail than what this short talk had time for, called the QML lecture series. Our event tomorrow is about kernel methods and kernel models.
Yeah, and we also have two more events in the series.
Yep. We also next year in January have a talk from NVIDIA. So
Yeah.
we have this lady from NVIDIA coming. She's going to be giving a talk on NVIDIA's ventures into quantum computation. And if any of you watched the GTC keynote, NVIDIA this year was announcing this thing called NVLink Quantum about how to interface GPUs with quantum computers.
Yeah, and so I know that Vinayak covered a lot over here, like single qubits, even like vector spatial, for example, right? All of those slides are available on our GitHub.
Yep.
So if you want to dive deep into the math, you can just check that out. And also like we don't have the recordings, but yeah, the slides should be helpful.
Recordings we are planning on releasing next semester after we do some like passes of checking on them.
Yeah.
So here, yeah, these slides are all available from the previous sessions. I'll have to upload, I think, one or two. Kostov actually did the talk in our last session. He was our guest speaker. He did a fantastic session on the ML basics part. The next announcement, again, if you guys found anything I was talking about here relevant, interesting, and you guys are fearless enough to take a difficult course at ASU, please do check out the course CSE 598 and CSE 494, depending on whether you're a grad student or undergrad. It's being taught by my advisor, Professor Aviraj Srivastava. And yeah, we're teaching quantum computation from a machine learning perspective.
Yeah, and I took it as a junior, so like just like you can do it. It's like not impossible.
And if you find me entertaining, I'm your TA. So yeah, with that, that's the end of the session. Absolutely open for Q&A. And as we go, one last self-plug. This is me, guys. Check me out. Yep, that's fine.